the Boltzmann distribution that we showed you yesterday, or last class, not yesterday, we can depict a distribution of particle speeds increasing from left to right, and sigma is the number of particles. So what it means is that like in this room, we have a number of particles, and some are at a high speed on this end of the curve on the right, and some are on the low speed end of the curve. But the issue is not all of the particles bumping around in this room have the same speed. I think that's a intuitively logic conclusion there. So how do we deal with the speed issue? We apply what is called a root mean square speed, as the title depicts, or the average speed of particles in our this is an approximation of where the average speed would be. Now, depending on the statistics applied, some will have an average a little shifted more to the right side of this. For what our purposes are, because see, you don't have a pure bell curve, it's shifted over here some. So in reality, this should shift over, but I picked the highest point in there, so it looks easier, okay? But you won't have to worry about calculating stuff relating to that. So, but in the idea of root mean square speeds, what happens is that a velocity can be changed for the particles by going to a different curve, or by increasing temperature or so, and you might have a curve that would shift to the right. And so these particles, which are low speeds, are now shifting over into here at T2. Now we'll make that T1. Well, to calculate the root mean square speed is a very easy formula. Root mean square speed is the symbol V with two little brackets, or some people will write in their literature RMS like that, and it is 3RT over mole weight. That is the formula. R being the universal gas constant. For our purposes, and that's what you'll find in the textbook. You'll find a problem that might change this, but I made it easy for you here. I want it in meters per second. Now you could get in there and play with it and get miles per hour if you want to, or whatever, but meters per second is the most widely used scientific velocity ratio, and it turns out to be 158 on the square root of the absolute temperature, that'll be Kelvin, over the mole weight. And some people will put a little n down there. Number average mole weight is what they call it. Temperature in Kelvin degrees, m, mole weight of particle. Could be an element or molecule, whatever you're interested in. This is a very simple problem, and the diagram I gave you a moment ago showing the Boltzmann distribution is where it really comes from, and what this RMS relates to. But as far as problems on the exams and stuff, this is the extent of that issue. All you have to do is know the formula. That's it. That is velocity, RMS, however you wish to subscript it, is 158 on the square root of Kelvin temperature over mole weight, and this will come out in meters per second. So it's a very simple calculation, and you could calculate this from any temperature, a given particle. What would its speed be over a range of temperatures? You can play with it and come out with some pretty interesting outcomes or compare speeds of, say, helium versus hydrogen, and so it's a real simple formula and can give you some comparative results very, very quickly. And in this problem, of course, we're dealing with hydrogen. Formula weight or mole weight is equal to 2 grams per mole, and the temperature is equal to 25 degrees Celsius, which needs to be in Kelvin temperature, 298. Now, when you substitute these in here, I have already solved the constants. And when you look at this 3RT, 3R, I converted and solved to a coefficient that, when multiplied by this radical and this ratio, will give you the meters per second. So putting this in, and the Kelvin temperatures will not say meters per second for you. It's all bound up in this 158. So the idea is you just substitute the absolute values and the mole weight values, and you will have the appropriate RMS speed. So that's 158 on the square root of 298 Kelvin over 2, and meters per second is the Graham's law of effusion. Okay, two terms here that are somewhat related: diffusion, and effusion. Diffusion is the random motion of particles within a container. If we had a container with a number of particles in here and isolating just one. Now, kinetic molecular theory says everything's always in motion, right? And we're to say at 25 degrees, and you can expect the air, like in this room, to be in constant motion. Well, if we take one of these particles and more or less track its pathway as it moves, we find it goes here, bounces off there, here, bounces, and just kind of goes and so forth in a random direction, but ultimately will migrate across the entire space. Example would be if someone brought in a sack of cheeseburgers and set them on the table right there, right after they've been fixed, and the people up front row would probably smell them very quickly, and the people in the back row, it would take a few minutes for you to smell the cheeseburgers. So that's what diffusion is. The odor molecules from the hamburgers takes a while to get to the back of the room, and that comes under the heading and definition of diffusion. Effusion is the discharge of a gas under pressure through a small opening. If you puncture the side of a gas tank for whatever reason, or some container that holds a quantity of gas under pressure, then I think you understand or know what's going to happen. If we have, say, a container that contains a gas under high pressure, that's capped, if you will, if you puncture that, then that gas is going to effuse. and it's called gas diffusion as it squirts out of the side of the container. Effusion is described by Graham's Law. And there are a couple of problems that need to be presented here. One is the time of effusion, and two, a comparative between the velocity of effusion of two different particles. But to understand that, you have to understand the velocity of effusion, and this is logical, is proportional to 1 over the square root of the mole weight, number average mole weight. So essentially, as we talk about this expression, the issue is inversely proportional. So if you want to, get a generalization, it's a comparative type of concept. Small particles, what's their diffusion, versus larger particles, what's their diffusion? Okay, since it's an inverse relationship, the larger the particle, the slower it effuses. Okay, that's the generalization. So increase mass, decrease effusion rate. Okay? Now, using this as a proportionality, we can convert it to an equation by inserting a proportionality constant times 1 over the square root of mole weight, like this. And solving for the K value, we find that the velocity of effusion is, K value is the product of the velocity of effusion times the square root of the mole weight, number average mole weight of some particle. Well, if we are comparing a couple of particles, particle 1, say, is sulfur dioxide, and particle 2 is sulfur trioxide, and they're both gases at the same temperature. The question is, which one will effuse the fastest? Well, the logic in there, as I said, this is a larger particle. But how much faster will the large particle go? Okay, if we assign for SO a K value, what does K mean? This is constant. It means the K value that we have assigned to SO2 is equal to the K value for SO3. So if the K values are equal, and K equals velocity of effusion of times the square root of mole weight, then we can put velocity of effusion times the square root of the mole weight of the SO2 is equal to the velocity of effusion times the square root of mole weight of the SO3. So all we have to do is calculate the mole weight and put it in here. I'll show you what I'm having to do here. Well, yeah. You don't even have to use grams per mole. You can just use it in terms of atomic mass units if you wish to do that. See, mole weight SO3. We just need one more oxygen, 64, 74, 80 AMUs. Okay. From this equation, you can solve for velocity of effusion of, say, SO2. Okay, and that would be this one. So velocity of SO2 is equal to the velocity of SO3 on the square root of the mole weight of SO3 divided by the square root of the mole weight of SO2. like that. It just came right out of here. Or we can velocity of SO3 to equal velocity of SO2 square root of mole weight of SO2 divided by square root of the mole weight of SO3, like that. So substituting in, what we have is a ratio. You'll see what I mean in just 1 second. SO2 was the square root of 64 divided by the square root of 80, and this one, velocity of SO3, is velocity of SO2 on the 80 over, did I get that right? 80 over 60 square root of. Okay. 8-9 times slower than SO2. The problem is essentially asking you how long, both of them have the same volume and are coming from identical tanks and stuff like that. How long does it take the Cl2 to effuse if you're given the one here, like in the problem says it's 30 seconds to effuse the nitrogen versus how long does it take the chlorine to effuse? Formula weight of N2 gas, of course, is 28 atomic mass units, and the formula weight of Cl2 gas equals 70 atomic mass unit. Chlorine significantly heavier. Okay, think with me on this. The velocity of effusion will be higher for the lower weight material, but its effusion rate, the time it takes for it to come out, is less than it would be for chlorine, because chlorine is bigger. So the heavier particle takes longer. Slower rate takes you longer to get to Cleveland, okay? So that's the idea. The heavier, the longer it takes you to drive the distance. So that's essentially what we're calculating here. Now, from Graham's law, we have velocity 1 on the square root of mole weight 1 equals to velocity number 2 on the square root of mole weight 2. And velocity is distance over time. I'll write it all the way out. And the distance, however, in this particular issue is the same for both of them. Both are transitioning the wall of the container. And so to make matters simple, we just say the distance is 1 over t. And so velocity is 1 over t. So we put that in here. So if V1, I'll come up here, V1 is 1 over time 1, and V2 is equal to 1 over time 2, then we could put those into the, substitute them into this expression, and we'd have the square root of M1 over time 1 is equal to square root of M2 over time 2. So it's an inverse relationship in this equivalence. Mass over time. Okay, you got that. And notice that mass of 1 is over the time of 1 equals mass 2 over time 2, and just square root the mass. And we're looking for time 2 right here. So we'll have time 1 on the square root of M2 over the square root of M1, like that. Be sure. T2 goes up, down, inverse, multiplication, yeah, right. Okay. Time 1 was 30 seconds. Square root of M2 is, what are we, 70, divided by M1, which is 28, and it'll all come out in seconds. Okay, it says 47.5 seconds. Well, the effusion rate for the smaller particle is 30 seconds, so this makes sense relative to increasing the mass, and getting a bigger particle takes longer to leave the